Hi and welcome everyone to part 4 of my video playlist about the best strategies for olefinating aldehydes. This presentation is about olefinations with geminal dihaloalkanes, with polar organometallics and with the aid of elemental titanium. Geminal dihaloalkanes are not readily available reagents, with the exception of halogenated methanes and acetic acid derivatives, which are prepared on a large scale. One way to prepare structurally more elaborate geminal dibromoalkanes is to treat aldehydes with bromine and a phosphide. Olefinations with geminal dihaloalkanes proceed by formation of either a dimetalloalkane or a carbene complex. Addition to aldehydes yields a beta-alkoxy organometallic intermediate, which undergoes beta elimination to yield an alkene. In this example, the nucleophile was generated from methyl trichloroacetate by treatment with metallic zinc and THF in the presence of benzaldehyde. These conditions can also be used for the methylation of enolizable aldehydes with dibromomethane. Dichloromethane is usually too unreactive for such one-pot olefinations, but it can be metallated twice under forcing conditions. In this experiment, dichloromethane was metallated by magnesium in the presence of an aldehyde, and a modest yield of the expected alkene was obtained. Because of the low reactivity of dichloromethane, however, a number of byproducts were formed. Pinacol dimerization of the aldehyde is a further potential side reaction. Generally, if dichloromethane is to be used as nucleophile, it should be dimetallated stoichiometrically before addition of the aldehyde. With more reactive dihalomethanes, however, one-pot procedures can give high yields. Chloroiodomethane, for instance, undergoes iodine-lithium exchange with methyl-lithium faster than the addition of methyl-lithium to aldehydes. In this example, the second metallation was effected by addition of metallic lithium, and 80% of the target olefin was obtained. A further strategy for the preparation of alkenes from aldehydes is by dehydration of secondary alcohols. This is not a very versatile strategy because in many instances regioisomeric olefins may be formed. Some secondary alcohols are also rather stable and require harsh conditions to eliminate water. Sometimes, however, this can be a practical approach for preparing olefins. Benzylic alcohols with an electron-rich arene eliminate water with ease, as shown here. A mildly acidic workup already caused a complete dehydration. Ether formation and Friedel-Crafts alkylation are potential side reactions. This is another example of the formation and dehydration of a benzylic alcohol. Good results were obtained with benzylic organozinc reagents, but with aliphatic nucleophiles, yields were lower when applying these conditions. Also with chlorotrimethylsilane as activator, no clean alkene formation could be achieved, and large amounts of secondary alcohol were obtained as byproduct. A further type of byproduct was the pinacol, resulting from a reductive dimerization of the aldehyde. For the preparation of 4-aryl butylamines, which are important CNS drugs, aldehydes or ketones must sometimes be converted into 4-aryl 1-halobutenes. This is best achieved by adding a cyclopropyl Grignard reagent to the aldehyde and treating the resulting alcohol with a hydrogen halide. In this example, the alcohol was activated by acetylation to protect the 1,3-diene from hydrohalogenation. With benzophenones or acetophenones as starting electrophile, though, this precaution is not required, and high yields of halobutenes will be obtained upon treating the cyclopropyl carbinol with hydrogen chloride or bromide. Aldehydes and ketones can also be converted into alkenes by treatment with elemental titanium in the so-called McMurray reaction. Best results are obtained when preparing symmetric alkenes, but numerous successful examples have been reported of the cross-coupling of two different aldehydes or ketones. It is assumed that this reaction proceeds by an initial pinacol coupling, followed by reductive cycloreversion and formation of the alkene and titanium dioxide. The conditions of the McMurray reaction are mild and enable the preparation of acid or base-sensitive products. Elemental titanium is usually generated by reducing titanium tetrachloride with zinc in THF, often in the presence of pyridine. If sensitive alkenes are the target, then a complete reduction of the strongly acidic titanium tetrachloride is important, and pyridine may help to buffer the reaction mixture. The most difficult part of this reaction is the addition of titanium tetrachloride to THF, whereby the yellow complex of THF with titanium tetrachloride is formed in a very violent and exothermic reaction. In this example, an acid-sensitive polyene was prepared by homocoupling of an aldehyde under the typical conditions of the McMurray reaction. In order to cross-couple two different carbonyl groups, it helps if one of them undergoes homocoupling only slowly. In this example, an aldehyde was coupled with an excess of benzophenone, and a fair yield of cross-coupled alkene was obtained. The partial cleavage of the Bock group may have been avoided by adding pyridine. So what are the typical byproducts of these reactions? As happens with all kinds of olefinations, occasionally the reaction stops at the alcohol stage. This can happen with certain types of aldehyde or if the reaction conditions were too mild. In particular, when using polar organometallics to olefinate aldehydes, the most important byproduct is often the secondary alcohol. Not all secondary alcohols eliminate water readily, and often the alcohol will have to be isolated and dehydrated in a second step. For instance, by treatment with thionyl chloride or phosphorus oxychloride and pyridine. Then, under basic or acidic conditions, enolysable aldehydes readily oligomerize and aldol condensation products will often be formed. If in a McMurray coupling too little reducing agent was used, unreacted titanium tetrachloride will strongly promote aldol condensations. Sometimes sterically shielded aldehydes are just reduced by carbon nucleophiles via single electron or hydride transfer. In olefinations with geminal dihaloalkanes, one potential side reaction is the cyclopropanation of the product. Carbene complexes sometimes cyclopropanate alkenes effectively, as for instance in the Simmons-Smith reaction, where cyclopropanes result upon treating alkenes with diiodomethane and zinc. I couldn't find any example of simultaneous olefination and cyclopropanation of an aldehyde, but in this example an indole was cyclopropanated during the methylation of a ketone. Then carbene complexes may dimerize, or the dihaloalkane may act as electrophile during metallation. Therefore, homocoupling products of the dihaloalkane should also be expected as potential byproducts. One potential intermediate of the reaction of metallated 1,1-dihaloalkanes with aldehydes is a 2-haloalkoxide. If insufficient metallating reagent is available, or if the reaction temperature is too high, then this alkoxide will cyclize and yield an epoxide, as in this example. During olefinations with polar organometallics, the intermediate secondary alkoxides are powerful hydride donors and may reduce the starting aldehyde to a primary alcohol. Ketones will result as a further byproduct. During McMurray reactions, pinacols are frequently obtained as byproducts, in particular if too little titanium was used. Pinacols may, however, also be obtained as byproducts during olefinations with geminal dihaloalkanes or other carbon nucleophiles. Polar organometallics are strong single-electron donors and can convert aldehydes into radical anions, which dimerize to pinacols. Electron-rich aldehydes, for instance donor-substituted benzaldehydes, are occasionally reduced to alkanes by elemental titanium. In this example, intramolecular McMurray coupling under high dilution gave only 1% of the rather strained target olefin. Despite the huge excess of titanium, the main product was a pinacol. Moreover, 2% of methylarene was also formed. Then, some electrophilic carboxylic acid derivatives can also undergo olefination in the presence of elemental titanium. Examples of the intramolecular olefination of esters by aldehydes have been reported, and in the example here, iptalimide underwent cross-coupling with benzaldehyde. On this and the next slide there are some more examples to help you get an idea on the scope of these reactions. You can also find this reference list in the description of this video. That's it. Hope you found this useful. On my channel there are also 4 videos about the olefination of ketones for further inspiration.